So today we're going to start chapter number 2, which is talking about radical transformations. So this is really going to build off of what we did in chapter 1, where we were just doing function transformations in general with a bunch of different types of functions. This one's focusing on radicals though. So we're talking about square roots and cube roots and all that fun stuff. Here we go. So today's plan, like I just said, starting chapter 2. This is a pretty short chapter. There's not too many lessons. As a matter of fact, I think there's only just 2 lessons plus a review day. We're going to deal with transformations just like all of chapter 1, except this time we're focusing on radical transformations, or radical functions. So in other words, root functions. We'll also investigate the effects of transformations on the domain and range of radical functions. Of course, any transformation you do will affect your domain and range. We'll get into that a little bit. And then lastly, we'll look at what happens when you straight up square root a whole function. Like you have a function, some old function, could be anything, whether it's a radical or not, and you're square rooting that entire thing. We're going to talk about what that would look like. Anyway, here we go. Let's get started. So radicals. Recall that a radical is a number that contains a root sign. That's about it, right? So in other words, if it has a square root, cube root, fourth root, whatever, it's a radical. Now, a radical function is an expression involving an input value x that is the radicand. So in other words, a thing underneath the root sign. The most basic radical function is the common base function f of x equals the square root of x. When we learned about inverse functions, that was in that last unit we did, we noted that the square root of x is the inverse of x squared. And this, of course, shouldn't really be a surprise because the inverse function undoes whatever the original function does, and thus a square root undoes a square. Whether that's important too much or not, it is just kind of nice to know. But anyway, moving on. So function transformations work on radical functions exactly as they work on any other type of function. So just like before, where we had like an a, b, h, and a k, that's still happening here. It's just your b times x minus h. That's going to be the stuff underneath the square root sign because we're going to compare everything to a base function of square root x. So in other words, the same function transformations that we had last time, whether it was vertical stretches, horizontal stretches, etc., they still apply. However, it is important to recognize that radical functions, at least those with even number indices, in other words, like a square root or a fourth root or a sixth root, they will have a limited domain. You cannot take the square root or any even index root of a negative number. So you can't take the square root of something like -4. It doesn't actually work. We can't do that, right? So in other words, because the stuff underneath your root sign, so if we went like this, square root x, because that stuff underneath the root sign needs to be greater than or equal to 0, we have inherently a limited domain. Now, of course, if we had like the square root of x minus 4, well, then that just means x minus 4 needs to be greater than or equal to 0. Or even better, just add 4 on both sides. We have x is greater than or equal to 4. Bottom line, what I'm trying to spit out is the stuff underneath the root sign needs to be greater than or equal to 0, right? Otherwise, you can't square root it. So we will just intuitively have a limited domain. Anyway, here's a first little example here. We're going to talk mostly just about transformations at first. For each of the following transformed functions of y equals square root x, I want us to describe the transformations. You can even see if you can do that first before we do anything. Sketch the graph of the transformed function. I'm going to help you with that. And then identify the domain and range of the transformed function. I can help you with that as well. At very least, if you could pause the video here and give this first point a try, that would be a good idea. All right, I'm going to go over that. So describing the transformations, just like a little bit of review from chapter 1. This thing on the outside, that's your vertical stretch. So I'm just going to straight up start by saying it's a vertical stretch, a vert stir by 2. The next thing we have is this minus sign in here. Good news is we have nested brackets, so we don't have to worry about anything there. But this minus sign here, that's your b value. Your b value in this case is -1. Now, b is usually thought of as your vertical stretch, or sorry, your horizontal stretch. So b is usually a horizontal stretch, but we don't actually have a number there other than like -1. So it won't be a horizontal stretch, it'll be a horizontal reflection. So I'll even write that in there, horizontal reflection. There we go. Now there's only one other thing that's happening to this other than like the square root of x, which is what we were basing this off of, and that's this -4. Just remember, because that's inside the function, that's going to be a horizontal shift, so a left or a right. Well, because it's x minus 4, it's going right 4. Now, here comes the second point. Sketch the graph of the transformed function. Well, just like before, when we were doing transformations of other functions, in order to sketch the graph of a transformed function, you need to know a little bit about what the original function looks like. I'm going to start by actually graphing this y equals the square root of x. Y equals the square root of x starts at 0, 0. And the reason I know that is because if you took the square root of 0, which is the lowest number that can go in here, you would just get 0. The next number I can put in here would be 1. The square root of 1 is actually 1. So that's all well and good. The next square rootable number I can put in here would be 4. So the square root of 4 is 2. So at x is 4, we have y is 2. And then the last number I can put in here is the square root of 9. Square root of 9 is, of course, 3. So those would be our points right there. And just for fun, I'll graph them. It's not a straight line. It's kind of a bit of a curved line here. Basically, it looks like a quadratic that fell flat on its side, right? Now we can't go any further back here because if you went below 0, you'd be taking the square root of a negative number. And we talked a moment ago about how that doesn't work. Anyway, bottom line is the reason I cared about graphing this original base function, you don't have to do it, but it helps. But the reason I cared about that is because now we have some points that we can compare to. Since we know in words a bunch of transformations that are happening to this function, we can turn these bunch of words into mapping notation and then move each of these points one at a time. That straight up is probably the easiest way of solving this. So let's do this. We'll set up our mapping notation here. Remember, mapping notation is where we say x, y becomes. Now let's think about what's happening to our x. You got to think of all the horizontal stuff going on, right? Well, we have a horizontal reflection and we're going right 4. Now remember, the mapping notation more or less follows exactly what you see in words. So if we do a horizontal reflection, that just means we're going negative x because we're flipping x over. So it's flipping over here. And then right 4, remember, this is very much backwards to what you see in like an equation notation. Right 4 means we're actually adding 4 to our x values because we want to make them bigger. For instance, if you had x is -6, if you're going right 4, you have to go 4 to the right. So you'd be at -2, right? So you added 4. Anyway, next thing, our y value. There's only one thing we're doing to our y value. That's a vertical stretch by 2. So we're going to go 2 times y. Now, I'm just going to change color just so we can show you that this is the new points we got going on here. Now I'm going to use this mapping notation and move each of these 4 original points to their new locations. I'm going to start with 0, 0. So 0, 0 on the original graph is going to become, if you plug 0 into x here, you're going to have +4. And if you plug 0 into y, you're going to have 0, right? Anyway, so I'll graph that 4, 0. That would be this point right here. Next one, we'll do 1, 1. Again, that was the next point on our original graph. 1, 1 is going to become -1 plus 4 is 3. And then 2 times 1, well, that's just 2. So we have 3, 2, 3, 2. That's right here. Then we have, what's the next point? I guess the next point we have is 4, 2. Yeah, so 4, 2. This is going to become, plug 4 in here. That's going to be -4 plus 4. That's 0. 2 times 2 is 4. So we have 0, 4. There we go. And then the last point I can plug in here is 9, 3. -9 plus 4, well, that'd be -5. And then 3 times 2, of course, is 6. So -5, 6. Awesome. So hopefully you can see it here. It's the arc, but it's going the other way. Of course, it's going the other way. We had a horizontal reflection. So if we just kind of arc this through, I'll do what I can do. Yeah, that's good enough. Good enough for me. It's pretty shaky, but you get the idea. Anyway, so we sketched the graph of the transform function. That one is all done. Awesome. Now this last point is identify the domain and range of the transformed function. Once you actually have a graph, holy smokes, the domain and range become no serious problem, right? If I were to do this without that, it would be pretty tricky. It's way nicer to have the graph ready to go. Let's start with the domain. So the domain of that new transformed function, the one I did in blue, think about when you think about domain, think about what your lowest x value could be. Well, the lowest x value we're going to have here is actually -infinity. So I'll say -infinity. And then my largest x value I'm going to have is +4. Then for my range, think about the lowest y value you'll have. Well, the lowest y value we'll have on the blue graph is 0. And we're going to include 0. So I'll put a square bracket. And then the highest y value will go, well, this is just going to keep on going. We have to assume it's going to be infinity. And there it is. So we got all 3 of those points there. Describe the transformations, sketch the graph of the transform function, and identify the domain and range. Let's do the next one here. Maybe you'll be able to do all 3 of these on your own. Remember, when we do that sketch the graph, we should be comparing it to the square root of x. I'm not going to draw both of them this time, but if you'd like, at very least, pause the video here and give that first point a try. All right, so I'm going to go over this to describe the transformations. First things first, hopefully you caught it. See this y plus 3 equals? Get rid of that +3 there. That thing's garbage. We don't want that there, right? You always want y by itself. It's ridiculous otherwise, right? It's just silly, just plain silly. You know what I mean? Anyway, what we're doing here, explaining all the different things that happen. On the outside of the square root, we have a negative. That means we have a vertical reflection. There's no vertical stretch amount because it's just -1. So we'll say it's a vertical reflection. Then we have a 2 in here. And notice we have nested brackets. That's good. We should have nested brackets. The 2 in here is our B value. Your B value is not your horizontal stretch, but it's related to it. So we'll say it's a horizontal stretch by not 2. It'd be 1/2. Right? These are always backwards to one another. Next thing we have here is in the brackets x plus 8. Well, plus 8 means we're going left 8. And then the last thing there, that -3 means we're going down 3. Awesome. Now, just like before, I'm going to use mapping notation to move all this stuff over. So I'm going to start by writing my mapping notation. This is x, y becomes, think about what's happening to your x. Use what you wrote in words. The stuff that's happening to x is the horizontal stuff. So horizontal stretch by 1/2. So it's going to be 1/2 x. And we're going left 8. I know how backwards this is going to sound, but that means we got to go -8. And then vertical reflection and down 3, that's happening to our y. So we'll have a negative y because it's a vertical reflection. And then down 3 is -3. Anyway, long story short, let's just throw in those points. We'll do the same points from before. Remember, it was 0, 0. Throw that in there. You're going to get -8, -3. I'll let you do those calculations on your own just so we speed this up. 1, 1. Throw that in there. That's going to give me, oh, that's trickier. That's -7.5 and then -4. If we plug in the next point, which was 4, 2, this is going to give me, hold on, 4, 2, that's going to be -6 and then -5. And then this last one here, 9, 3, this is going to become, if you plug 9, 3 in there, you're going to get -3.5, -6. Plot these points on here. I know it's really weird having some 0.5s, but it is what it is. Anyway, -8, -3, there we go. -7.5, -4. That looks like it's about right there. -6, -5. So -6, -5, that would be exactly here. And then -3.5, -6, that would be down here. And then connect that. We're starting at this point. We're connecting the rest with a line. And that's going to continue off somewhere like that, right? Now, the reason I don't draw anything further past this point right here is because this point is basically branching off of our vertex. Our vertex originally was 0, 0. And nothing came before that. Like on the original function from before, it looks something like that. That's a very cheap drawing of it. But remember, it started there. So if this thing has been vertically reflected, so flipped upside down, stretched by 1/2. So in other words, it's really compressed here. This part here was compressed by 1/2, moved it left 8 and down 3. That's where that thing is going, right? It's not gaining more stuff on the other end. Okay, hopefully that makes sense. If it doesn't, well, you'll have to come ask, but it is what it is. Moving on, next page. Write the equation of the radical function that results from applying each set of transformations to the graph of this. So vertical stretch by a factor 4, reflection in the x-axis. Hold on, reflection in the x-axis, that's a vertical reflection. Translation of 1 right and then 3 down. So we want the equation here. So we want like actual equation notation. As silly as it might be with this, because it's a relatively simple base function, I would still start with function notation. Function notation in this chapter, it's the same as it always was, right? You just use that, that general form. So the general form says y equals a, which is your vertical stretch. Well, vertical stretch is 4, but we also have a vertical reflection. So I'm actually going to make that -4. And then f, square bracket. Do we have a b value? I don't think we do. There's no word there about a horizontal stretch. So then I'll just do another bracket. X, we're going right 1. So it's x -1 and then 3 down. So then -3. So now that we have this in function notation, we can jump to equation notation. And this one's not too crazy. Notice inside the function, we have the f and then our square brackets. This stuff inside the function is what replaces your x in your original base function. So I'll say it again, the stuff inside the square brackets, inside the f here, replaces your x. So I'm going to start with that. I'm going to say y equals, let's replace the x in there. So this is going to be the square root of x -1. So that stuff in there, replace the x. All this stuff on the outside just gets tacked on afterwards. So this -4 or -4 times f of x and all that, that's just going to be tacked on out here. So we have a -4. And then this -3 is also just tacked on to the very end. Next one here, horizontal stretch by a factor of 1/4, blah, blah, blah. Okay, anyway, long story short, we're going to have our function notation. Y equals, do we have a vertical stretch? Doesn't look like we do, and we don't have a reflection across the x-axis. So we got no a value. I'm going to jump right to f then. This is f, square bracket. We have the b value, which is related to the horizontal stretch. Since this is a horizontal stretch by a factor of 1/4, remember the b value needs to be that flipped around. So it's actually going to be a b value of 4. But wait, then we also set a reflection in the y-axis. Well, that's a horizontal reflection, so it'll actually be -4, right? Then we do our nested bracket. X, we're going left 7, so x plus 7. End the bracket off, and then we're going 1 up, so +1. Perfect, right? Now, equation notation, we take the stuff inside the f, so inside these square brackets, and we replace the x that we had from before. So this is going to be y equals the square root of -4x plus 7, and then the stuff on the outside gets tacked on afterwards. So then we just have a +1 on the outside. That was all there was to that, right? Really, really, really important to understand that function notation always looks like the same thing. You just always use the same function notation. And once you have that, you can jump to equation notation just by starting by plugging in the stuff inside of f into wherever x was. If you have more than one x inside your actual base function, you just got to plug this in more than once. It is what it is, right? Moving on. Question 3. This one's a weird one. Part B is absolute baby food, but part A is pretty weird. The speed of sound in dry air can be found using the formula that, where S is the speed of sound in meters per second, and T is the air temperature in degrees Celsius. Determine the domain and range. What is the contextual significance of this domain and range? Here's what I'm going to tell you. You get 2 options for finding the domain and range. Remember earlier when I said, oh, having a graph makes it so much easier. Well, graphing this just by pen and paper might be a bit tough, but you have your graphing calculator. So your first option here is just throw it in your graphing calculator and then see what the graph looks like. You'll have to change your window, of course. See what the graph looks like and find what your minimum value of x, and x in this case would actually be t. Find what the minimum value of that is and find the maximum and go from there, right? That's an option. Here's another option though. Since this is a square root graph, right? It's a square root graph. Your domain is limited by the fact that this underneath the root sign has to be positive. Let me write that out. So that means 1 plus t over 273.15. That's an interesting number. For those of you who've taken chemistry, you might actually know what that is, but I'll save that for later. Anyway, 1 plus t over 273.15. That thing needs to be greater than or equal to 0. Because if it wasn't, you'd be square rooting a negative number, and that's not a good time, right? Anyway, let's solve for t. Let's figure out what t has to be here. So I'll subtract 1 on both sides. This gives me t over 273.15 needs to be greater than or equal to -1. Then multiply by 273.15 on both sides. So this just means t needs to be greater than or equal to -273.15. That right there, that is actually your domain. Your domain is that your t, your temperature, has to be greater than or equal to -273.15. Now, before we move on to range, we can actually talk about the contextual significance of that domain. By contextual significance, it just means, given the context of this question, speed of sound and air temperature, why does your T, your temperature, have to be greater than or equal to -273.15? Well, some of you may know, others, if you're not taking chemistry, I wouldn't blame you. But the answer to that is temperature in general has to be above that. This number, -273.15, that's actually absolute 0. You can't go below that. Like it's not possible to go below absolute 0. So in terms of the significance is your temperature, I'll just say your temp can't drop below absolute 0, right? It's not possible. Anyway, moving on. Now we'll deal with our range. In terms of our range, the lowest value of our y value, which is our speed, is going to happen when this square root equals 0, right? Because like what we just found right here, if t was equal to -273.15, you would have this 0, right? That's what would happen. And you can't go below that because there's no way to make that negative, right? So because the lowest that square root can go is 0, that means the lowest this function can go is 331.3 times 0, which of course is just 0. So guess what? We get to say speed needs to be greater than or equal to 0. And that right there, because s was your y value, that is your range. Now, what's the significance of that? This one is a lot more clear if you think about what that means. Your speed of sound has to be greater than or equal to 0. Well, I sure hope it does. Imagine if your speed of sound was a negative number. If your speed of sound was a negative number, what does that mean? Your sound is going backwards first? It doesn't mean anything, right? So I don't even know what to write here. It's just speed must be positive. That's all that really means. I'm butchering my writing here. Anyway, there we go. Anyway, speed must be positive. Okay, question B. I almost actually considered just taking this out of here, but it is what it is. Determine the speed of sound at the nearest whole meter per second if the air temperature is 20 degrees Celsius. This literally just means you plug 20 into this. So use your calculator, plug it in. I'm going to save us all the trouble. I'm going to just say S equals to the nearest whole meter per second, 343 meters per second. Anyway, I'm not going to waste any more time on that one. Moving on. So here's one of the beefier things today. This is a good one, actually. Square roots of functions. So we're moving on to like a little bit of a different topic here. We're going to square root a full-blown function now. So we're going to play around with this first. I want us to start with a nice linear equation. So on the grid provided, draw the graph of the function f of x equals 1/2 x plus 1. That's just a linear equation, right? There's no x squared, no x cubed, nothing. So it's going to be a straight line. Just to remind you how we graph a linear equation, I always start with my my plus whatever. That's your y-intercept, right? So that means I'm crossing the y-axis at +1. So I'm going to put a dot right there. As for this 1/2 times x, well, 1/2 is your slope, right? Slope is often known as rise over run. That just means I'm going to go up 1 and run 2, and then up 1 and run 2, up 1, run 2, and so on, right? If you want to go backwards, go for it. You just go backwards 2 and then down 1, backwards 2 and then down 1. The more the merrier here. It is what it is. Anyway, graph that with a line. There we go. That was actually not too shabby. Anyway, so that's our line right there now. So then it says complete the table of values for g of x equals the square root of all that. Use the table to help you graph g of x on the same grid. Okay, so what it wants us to do here is plug in all of these values of x into our g of x. So this is for g of x right here, right? Maybe I'll change color because we'll make this red, right? So g of x is what we're plugging in here. So if we plug x is -4 into this, I mean, I'll save you the trouble. If you plug that in there, you're going to get a negative square root. So that's not going to work. So no answer, right? NA. If you plug in x is -2, 1/2 times -2 is -1. -1 plus 1 is 0. Square root of 0 is just 0. Interesting, right? Anyway, next one, 0. If I plug 0 in here, we got the square root of 1. Well, that's just 1. Then these ones are a little messier. If I plug in 2, it's going to be 1/2 times 2, which is 1. 1 plus 1 is 2. The square root of 2 is a terrible number, but I'm just going to round it to 1.41. And then same with 4. You plug 4 into this, it's going to be 1/2 times 4 is 2. 2 plus 1 is 3. Square root of 3 is 1.73. I just saved you the trouble. Anyway, it wants us to graph that on the same grid. So at -2, we have 0. Well, that's interesting. That's exactly where we were on the other graph. How funny is that? What about when x is 0? Well, y is 1. Hey, wait a minute. That's the same as one we had there. Well, things are going to get different real quick here. So what about when x is 2? When x is 2, we have y is 1.41. Well, that's about right here. So now we're below the graph. That's interesting. What about when x is 4? 1.73. Well, x is 4, 1.73. That's about up here. Quite a bit below the graph now. So this graph is looking like it's kind of like taking a bit of a curve here, right? Now, the real question is between these 2 points, are we going to be above this graph or are we going to be below this graph? You know, we can see it curving this way. So wouldn't you think it's going to curve above it? I don't know. I guess we can prove this. Let's plug in x is 1 just for fun. Or sorry, x is -1. X equals -1 just for fun here, right? So if we plug in x is -1, you got the square root of -1 times 1/2 is -1/2. -1/2 plus 1 is the square root of 0.5. I'm going to be real here. I didn't calculate this before I started doing the video. Let me try this though. The square root of 0.5, well, that gives me about 0.71, we'll say. 0.71, that's my y. So when x is -1, then y is 0.71. So -1, 0.71. That looks like it's about here. I'm gonna safely say that we're going to be above the graph there. But then after this point, we're going to be below the graph. Weird, right? So a really weird shape to the graph, right? The square root of this original graph is we like started at the same like x-intercept, and in this point over here, we also had the same, but then we were above the graph for a little while, and then we were below the graph everywhere after that. Really, really strange. Let's talk about that for a second though. What were the coordinates of any invariant points? Well, if we go back, remember I said we had a couple points that were the same. Well, the coordinates of those points were -2, 0 and 0, 1. Now I'm going to make something really clear for you. I don't believe in any baloney on this kind of thing. This stuff is weird, but it's not actually as hard as it might seem. There's a trick here. These invariant points are actually invariant points for a very special reason. These are invariant points because y is equal to 0 and y equals 1. Think about it this way. Remember how we always said, oh, f of x is your y, right? And if we're square rooting f of x, that just means we're square rooting your y. Well, here's a question for you. What's the square root of 0? Like if y was 0, what's the square root of 0? Well, I hope you said to your screen just now, it is 0, right? What about the square root of 1? Well, what the heck? That is 1 as well. Holy smokes, right? Big surprise, right? So bottom line is, when you have on your original graph, y is 0 or y is 1, if you were to square root that whole graph, those points are not going to move. Anywhere where y was 0 and y is 1, those points aren't going to move. Now here's the real kicker though. For which values of x is the graph of g of x above the graph of f? Well, if we look, the values of x would be between -2 and 0. So I'll even just write that in words. Between x is -2 and x is 0. Now these x values, it's just a coincidence. Just notice that this is also just so happens to be between a y value of 0 and a y value of 1. When you're square rooting a number that is 0 point something, so in other words, a y value that is between 0 and 1, well, when you square root a number like that, it actually goes up. Like for instance, the square root of 0.5, we notice that that's 0.71. The square root of that number is bigger than the number itself. You can't do that for anything else. The square root of everything else always goes smaller, but not for those numbers. The 0 point something, they actually get bigger, right? So when you are between y is 0 and y is 1, you square root that, you're going to be going above your graph. Now, for which values of x is the graph of g of x below the graph of f of x? Oops. Well, pretty much everything else, right? Well, we don't exist down on the left side here, but pretty much everything bigger than 0, then yeah. So for everything x is greater than or equal to 0. Well, I guess we just say greater than 0, not greater than or equal to, but it is what it is. Anyway, so that's all we got there. So just some tips. Taking the square root of a function, there are a few important observations to make regarding any radical function. G of x equals the square root of f of x. So when we're square rooting a pre-existing function, here's the first thing. The domain of f of x, or sorry, the domain of g of x will be limited to the x values that make f of x greater than or equal to 0. The reason for this is if we're square rooting f of x, we need to make sure we're square rooting a positive number. So in other words, it's just going to be where your y values are positive, like we saw in this case here. The other thing we'll notice, invariant points will occur where f of x, remember that's a fancy way of saying y, f of x equals 0 and f of x equals 1. And this again is because if you square root this and you square root this, you still start off or finish off rather with the same thing you started with. The next thing we got to know from this is the y values of g of x will always be below the y values of f of x, except between where f of x is 0 and f of x is 1. So in those ranges there, just because when you square root a number that is 0 point something, it actually grows. Everywhere else it'll be below the original graph. So all that's really happening when you square root a function is that the y values are being square rooted. That is it. That's all we're doing. We're just square rooting our y values. Nothing else, nothing too special. This does, however, produce a somewhat interesting shape to the new function, as we saw here. We had a very boring blue linear function. When we square root it, it does something kind of interesting. It definitely sits kind of on its side there. All right, so here's a couple examples. We're almost done here today, so this shouldn't hopefully take too much longer. This first example is a bit of a weird one because this time around, we're not going to be dealing with just a boring linear function. Notice that f of x here is a quadratic. So first things first, draw the graph of the function f of x, and then we want to draw the graph of the function, oh, this got chopped off, should say g of x equals the square root of f of x. And then we'll state the domain and range of f and the domain and range of g. If you want to pause the video here and give it a try, by all means you can. Otherwise, I'm going to go over this. First things first, I'm going to focus on doing this graph right here, f of x. You might look at that function right there and go, oh, I don't even know where to start. Hopefully you remember from the last unit, just think of f of x as being in itself a translation of x squared. This is just an x squared function that has a -1 on the inside of it and a -9 on the outside. Well, think about what this -1 does on the inside of a function. That should be a right 1. This -9 on the outside, that moves it down 9. So we're just taking x squared, and literally the only thing we've done to it is we've moved it right 1 and down 9. So I'll start by graphing that. Right 1, down 9. We're down here. You remember how to graph a quadratic like x squared? It's just the 149 rule. That's where you go over 1, then up 1 times a. Well, there's no a value here. So we're going to go over 1, up 1. Then we're going to go back to the vertex, go over 2, up 4. And then go back to the vertex, go over 3, up 9. That'll take us here. And then just make it symmetrical on both sides. And you know what, just for fun, sometimes you get to do the really rare thing. There's 1, 4, 9, but then the next number after that is 16. We can actually go up 16 here as well. If we go up 16, that'll take us up to here. So why not? What the heck? Might as well go that far. Connect this with as nice of a curved line as you can. Try not to butcher this as I say as I butcher it. There we go. What about this side? No, 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 that was too much. That was too much. Trying that again. Here we go. Doing this. Hopefully you're filling this in better than I am. Want to get that nice and accurate there. Perfect. Perfect. Awesome. That'll be good enough. This stretch right here, though, I want to just fix because that wasn't as accurate as I was hoping. There we go. That's a little bit better. Not perfect, but I think a little bit better, at least for what I'm going to need it for. Anyway, so that's f of x done. F of x is done in red. Now for the real fun part, we got to do the graph of g of x, the square root of f of x. Well, let's use exactly what we learned before. See these points right here? How about I just like clear all this so we can actually read it again? See all these tips and tricks of the trade before? This stuff is going to be really, really useful. The domain of g of x is just going to be where f of x was greater than or equal to 0. So in other words, we only care about this stuff that is positive. All this stuff that is underneath the x-axis, all of this stuff that's down in the negative, we don't care about it because we can't square root that. It's all negative values of y. We can't square root those. So we're only going to care about this positive stuff here. The second thing is invariant points will occur where f of x is 0 and f of x is 1. Again, that's just a fancy saying y is 0 and y is 1. Let's look at where y is 0 and y is 1 here. If we're going to focus on y is 0, that's just the stuff on the x-axis. That means we're going to have a point here and a point here. If we focus on where y is 1, that means we're going to have a point here and a point here. There we go. Those are going to be our invariant points. The last thing we got to keep in mind is that the y values of g of x will always be below the y values of f of x, except between where f of x is 0 and f of x is 1. In more plain English, on your graph, this blue graph I'm going to draw for the square root needs to be underneath this red graph everywhere, except between y is 0 and y is 1. So between these 2 points, we're going to be above that original graph. And I always draw it with an exaggeration, just like a big lump like that. Everything else after that is going to be below the function. Now, if you want to do this really accurate, pick some points that are easy to square root. What about y is 4? We can square root that, no problem. Y is 4, well, the square root of 4 is 2. So where y is 4, that's right here on the original graph, that's going to become 2 on this one. So just go straight down from there, plot a point at 2. Same on this side. Y is 4, square root that, it's 2, just bring it straight down, put a 2 right there. Another point that's easy to square root would be 9. Look at where we have 9. 9's up here somewhere. I don't think I did that one very accurately. I think it's supposed to be a little bit to the right of that. I'm going to pretend it's over there. Square root of 9, though, is 3. So we're going to have that about right there. All right. This one looks a little bit more accurate. 9 is about right there. Square root of 9 is 3. We'll put a point right there. So if I'm going to finish this off, it's just going to look like this. Whoosh and whoosh. Does not need to be super accurate. I'm just making sure that you know that the square root of this function is below the graph, except in these regions right here. Now, for the fun part here, state the domain and range of f of x. Let's start with f of x, of course. So for C, f of x domain. Looking at the red function, f of x, looks like you could plug in whatever you wanted for x. So guess what? I'm going to say my domain. You could do this. You could say negative infinity to positive infinity. Or if you prefer, you could just say x is an element of the real numbers, whatever floats your boat, right? Anyway, as for a range, this one's a little bit spicier. What's the lowest our y value could be on our red graph? Well, it looks like the lowest we can go is -9, so I'll say -9. And then what's the highest our y value could be? Well, that's going to go up forever, so it's going to be infinity. Another way you could say this is just y is greater than or equal to -9, whatever floats your boat. Last part of this question, D, wants a domain and range of g of x. The domain is going to be really weird. Notice the lowest our x could go is -infinity. We're talking for the blue graph now. The lowest our x could go is -infinity. The highest it could go to this point is -2. But then there's like a big gap where we don't have anything. And then it starts again at 4 and goes all the way to infinity. Here's how we write that. My domain for that blue graph is going to be negative infinity to negative 2 inclusive, so square bracket, and square bracket again, 4 to positive infinity. So what this means is we go from negative infinity to negative 2, and then after a little bit of a pause, we go from 4 to positive infinity. There you go. Range, this one's not nearly as interesting. What's the lowest our y value can go on these blue graphs? Well, the lowest our y value can go would be 0. So 0. And then the highest our y value can go, looks like it's going to go up forever. So infinity. Woo, there it is. So quite a bit of a process, but the bottom line here is once you have your original graph plotted, just basically find where y is 0 and y is 1, put your invariant points on there, draw a little blip above in there, and then go below everywhere else. To make it a more accurate graph, just find easy to square root y values like 4 or 9 or 16 or anything like that, and just plot them on. That's all you got to do, okay? Last example of the day, here we go, and then we'll do a quick summary. Given the graph of the function y equals f of x, so it gave us y is f of x, sketch the graph of y is the square root of f of x. Well, holy smokes, this is just like the last one, except this time we don't have to draw the original graph. It gave it to us, gave it to us. Ugh. Anyway, I highly encourage, pause the video here and at very least think really critically about where you're going to draw this graph. All right, you better have thought really hard about this one, by golly, I'm telling you that much. So here we go. What we got to do is, first of all, identify where y is 0 and y is 1, because those are going to be our invariant points. So y is 0 is here, y is 1 is right there. Those are our invariant points. Those aren't moving. Next thing I do is I draw a little lumped line above the original graph between those 2 points. So between y is 1 and y is 0, I want to draw a little bump above the original graph, so it'll look something like this. There we go. That's all I had to do, just a little bump above the original graph. And then just to make everyone happy for the rest of this function, pick some y values that are easy to square root on your original graph and square root them. Well, 4 is right here. So 4 is about right here. Square root of 4 is 2. I'm going to put that right there. So 4, 2, straight down, right? Next one would be 9. It looks like it's literally the very tip of this arrow here is up at y is 9. So if that's the very tip of the arrow, and we're going to square root 9, that's going to bring us down to 3. Just trying to line it up with the other one. There we go. It's going to be there. And that's going to be our next point. Doesn't look like we can go any further than that. So I'm just going to connect this with a bit of a curved line. And it goes on and on and on forever. That's it. It's not even looking for domain and range. That's all we got to do. So to summarize today, on the graph of f of x and square root of f of x, there will be invariant points wherever y is 0, you got to fill that in your notes, and y is 1. There you go, right? So those are your 2 things to fill in your notes. Now, the graph of the square root of f of x will be below the graph of f of x. So your square root function, which on this picture that I threw in, I know this picture's not in your notes, but it's just for fun. On this picture, the square root function is the blue one. It'll be below the graph of your original function when y is greater than 1. You could also say f of x is greater than 1, whatever floats your boat, right? So notice blue is below red everywhere after y is 1, right? Okay, everywhere, like in terms of our y distance, everything after that, right? As for the graph of the square root of f of x being above the graph, well, that's just between y is 0 and y is 1. And again, you could say f of x, whatever floats your boat. And then last but not least, this one's a total buzzkill, but if you are interested in mapping notation, the mapping notation for square roots of functions is just baby food. You're just taking x and y and you're turning it to x square root y. You're just square rooting your y values, as we saw on this last graph where I just square rooted my y values. I seriously just brought them right down. That's all. Okay. Anyway, so that's it for that. Hopefully you got all that in there. For practice, you got 2 sets of questions, plus you're going to get a chapter 2 homework booklet. So make sure, of course, that we're trying all of these questions. You do need to keep up on this stuff. This is a very fast-paced course. If you have any questions, please let me know.